So collisions are a key problem with hash tables, and if we don't have methods to tackle this problem, a hash table is practically unusable because we always run into issues. So today I will be showing you guys some very powerful techniques to deal with collisions. In the last video I showed you guys how hash tables work, and we had this specific example of a collision. What's happening here is we've got a key called age we're trying to insert into the hash table, and it maps to the index of 0. However, the name key value pair is being stored there. So what's happening is we're trying to store multiple key value pairs in the same index, and this is known as a collision. Another definition of a collision you might find more intuitive is when two or more key value pairs map to the same index. So how can we solve this? Well, instead of looking at collision resolution techniques, we might want to take a step back and see why are we having collisions in the first place. One reason is we have a poor hash function. A hash function's job is to create unique hashes which are different enough so that the likelihood of having two or more key value pairs mapped to the same index is low. So if you have lots of collisions happening, it could be that our hash function is quite poor because it's not generating unique hashes. Now the simple solution is we can choose a better hash function. And there are lots of different hash functions online like meow hash, city hash, murmur hash, Jenkins, a lot of other really good ones I haven't mentioned, but you can look online and you can use these hash functions and see if this reduces the likelihood of collisions occurring. However, if that didn't fix it, what might have happened is our hash table is too small. If a hash table is too small, then it doesn't matter how good our hash function is, because there's a high likelihood that the indexes will be mapped to repeatedly. And a technique we can use to deal with a small hash table is rehashing. So if we look back at the example I showed you guys before of this age key value pair we're trying to add, what we can do is we can rehash all of our elements. What I mean by that is we're going to first remove all the elements from the hash table. We will then make the hash table bigger so we have more indexes that we can store the data in. We will then rehash all those elements we took out previously, and now they may have different positions, so rehash them and map them to the new indexes. Now if I try to hash the age key value pair again, or the age key, I get a hash of 9479. I run modulus 6 on it, that should have been a 6. It gets mapped to 4. So then I store the key age at 4 and the value 19 goes with it. So what happens is by making the hash table bigger, we have more indexes the hash function can be mapped to. So the hash value can be mapped to. So it reduces the chances of a collision occurring. Now let's say we don't want to deal with this. Let's say we have a very large hash table, or is large enough for our use case, and we also have picked a good hash function, so we know that the hash function is not the problem. What can we do then? Well, what's happening here is we're having collisions occurring, and we need to be able to deal with the collisions in place. One technique we can use is called separate chaining. Separate chaining works in an interesting way. So let's bring back the example we had. I hash age and I get the index of 1. One is being stored, one is already being occupied by the key value pair surname. So what we can do is I can turn surname into a node of a linked list. Now if you guys know how linked list works, we have a node and the node holds a pointer to the next node or the next element in the linked list. And then I can create the pointer to the next element of this linked list to be age, right? And age is another node with the key value pair, which is a key value pair. So what we've done is we've introduced an external data structure, or rather we've added another data structure, which is a linked list, to store our data. And this is very powerful, as you can think, because we can have many collisions and all we have to do is just add a new node at that index and we've dealt with it. However, this does come at a cost, which is if we have lots of collisions occurring and we end up having a very large linked list, if you want to add or remove an element, then we have to traverse a large majority of the linked list to usually find the element if it's been recently added. And if you guys know anything about traversing linked lists, it's a very slow process because we can't just hop to a specific index. We have to go to each element one by one and follow the chain of pointers. So let's say we don't want to do this process of adding an external data structure into the hash table. We instead want to store the data in the hash table itself. We can use a technique here called linear probing. Now, linear probing comes under a family of techniques which comes under open addressing. So we have open addressing is this style of collision resolution where instead of adding an external data structure to hold our data, we instead store all the data in place in the hash table. And linear probing is an example of one of these techniques. We also have other techniques which fall in this category, like we have quadratic probing, we also have double hashing, and many others, but they all work in a similar way as linear probing. So by explaining this one algorithm, you guys should have a very good idea of how the other ones work, because they're just making little changes on this idea to make it more efficient. So what do I mean by storing the data in the hash table itself? Let's bring back the example we had. Age maps to the index of 1. Now 1 is currently being used by the key surname. So what we can do is we can look at the index next to 1, which is 2. 2 is empty. So what we can do is we can store age at position 2 and the value 19 will go with it. What have I done here? The process of linear probing is I first check the index I want to store the data at to see if it's empty. If it's empty, that's great, we just put the data right in. If it's not empty, it's being occupied, such as in this case, being occupied with surname, I check the next index underneath it. So in this case it was 2, and if that index is empty, we add it there. If the index is not empty, we go to the next one, the next one, the next one, and see if there's any empty space in the hash table. If there is space, we'll just store the element there. If there's no space in the hash table, it's completely full, then that means we can't add any more data to the hash table. Now, something you might be thinking is, okay, so I'm adding the key value pair, the next available index, but won't that make everything a lot slower? By slower, I mean, let's say we want to index an element, and then we first we check where we think it's going to be according to the hash. It's not there. We search the next element. It's not there. We keep on searching, and somewhere far down in the hash table, it's being stored there. And this is a problem, right? This is a problem as the hash table gets larger and larger. It can take, in the worst case, an extremely long time to find this key value pair because you have to go through all the elements in the hash table. There are ways we can mitigate this, such as with quadratic probing and double hashing to some degree. They can reduce the likelihood of this happening. But this is still a problem with open addressing techniques, is that we have to end up searching the hash table repeatedly to find the key value pair if it's not stored where we expect it to be. So this is kind of the basic collision resolution techniques we have. If you guys want to know more about double hashing and quadratic probing and other open addressing collision resolution techniques, I'll leave a link to an article in the description. You guys can read that. But they kind of work in a very similar way to linear probing, just that they work slightly differently to make it a bit more optimal. So now I will write down an implementation of separate chaining in C. So here I've got the code from the previous tutorial where we made a hash table, and I'm going to start to modify it so we can have collision resolution techniques, particularly separate chaining. So the first thing I'm going to do is change the hash table struct. I'm going to remove the key value arrays, and I'm going to instead replace them with a hash node struct. So here I've got a hash node, and what I'm going to do is we're going to hold an array of hash nodes right here. I'll call it data. So I'm going to also rename I'm going to add some parameters for the hash node. So it's going to have a key, it's going to have a value, and it will have two pointers. So it's going to be a struct hash node pointer to the parent node and a pointer to the child node. And I'll explain why I'm doing this in just a sec. So the way I'm implementing this is as a doubly linked list. That means that we can traverse the list forwards and backwards. So we can go from one node to the next and also go backwards to the previous node it came from. And this allows us, this property is very useful for removing nodes at some middle point in the linked list. What I mean by that is, let's say I've got a node and it has a parent and a child, so it's in the middle of a linked list. I can move the pointers around so that the parent now points to that node's child, and then I can just free the memory for the node I'm trying to remove. This may seem quite abstract right now, but once I start writing the code down for it, it should make a lot more sense, hopefully. So now that we've got this new structure added, I'm going to start changing the code right here for initializing the hash table. So instead of initializing the keys and values, I'm going to initialize the data as an array of hash nodes, and then I'm just going to multiply that by count. And then I'll just memset all of that data to 0. So we'll do it right here, hash node, I'll just memset it to 0. The gen hash function is fine. I'm going to start to modify the hash table add function. The first step is understanding, okay, what are the conditions where we're adding some piece of data into the hash table. So let's say this index which I'm visiting, the key is set to null. So right here, the key is set to null. What does that mean? It means that no other key value pair has been stored inside of this linked list, so it's empty. This is the first node. So in the case that the key's index at this point is equal to null, then what we can do is I can just say hash table of keys, hash table at data key, right? I'll just set this to be equal to a hash node, just initialize it this way. So I'll say key is equal to stir duplicate key, and value is equal to stir duplicate value. The parent node is going to be equal to null, and the child node will be equal to null, because this is the first node in the linked list, so it's not going to have any parent or child node right now. When we add new nodes, so we append it from this node, then we can manipulate the parent-child variables. So the reason I'm using stir duplicate here instead of just doing key is equal to key is because stir duplicate will allocate memory on the heap to store a new string, and they will copy this string that we provided, so in this case key, it will copy that into that buffer and then node terminate it for us. So we've got a separate key that we can have. The reason this is important is because this key the user provided, they might have allocated that themselves, and they may free at some point in time, and we don't know about that. So if we just create a pointer to the key directly, we have the risk of running into null pointers or accessing freed memory if the user decides to free it at any point when we don't want it to be freed. So we're just creating a copy of the key here for our just showing the data structure. And if this is successful, we just return true. Now in the case that, I'll just remove these two lines. The other case we can have is that we are appending a node onto a linked list. So at this index, if the key is not equal to null, the first node, that means that there's only data being stored at that index. So we have to add a new node at the end of the linked list. The way we can do that is by traversing through the whole linked list. So create a hash node variable right here. I'll just say that's hash table at data of index, right? And then I'll create a for loop here. So while hash node's next, or rather not next, while the child member is not equal to null, we'll just go to the node's child. After running this for loop, what will happen is you will traverse through the whole linked list until we're at the last node in the linked list. So this node has no valid child node. What this means we can do is we can say the node's child, we can allocate memory for a new node right here, say size of hash node, and then we can initialize data for this child node. So we can say child node, I have to dereference it so we can specify its values. We'll have a key of this. I can just duplicate the code right here. So the parent node will be equal to our current node, right? Because we're actually modifying, we're changing the attributes of the child node from the parent node. So this allows us to do this thing right here. So the current node we're at, that's going to be the parent node, and the child node we're changing right here, we can just set the variables for it. And the parent node will be set to node, and the child node is set to null because we haven't. This is the end of the linked list. We just set child node equal to null, and then return true once again. And in the case that neither of these if statements are fulfilled, that means that we can not add the node into the hash table, which will never happen because, as you can see, this else statement will always succeed. So we don't actually need this, but the code will give us a warning saying that there's an undefined return path, undefined path where we can return from. So I just add this here to avoid the compiler making warnings. The next function you have to fill out is the hash table get value at key function. So let's think about this carefully. If the index is equal to null, right? Actually, let's say if the index is not equal to null, we'll check this first. So if the index is equal to, if the key at this index is equal to null, that means that no data has been stored at this node. So the linked list is empty, so there's no data there. In that case, we can just return null. So we just return null here if this if statement does not succeed. If this if statement does succeed, then we have two conditions that could be happening right now. Either A, we have just one node inside of this linked list, which matches which contains the key we're looking for, or if it doesn't, it might be some other member in the linked list. So we have to traverse through the whole linked list to find it. So what we can do here is we say hash node is equal to this. Then as long as the current node is not equal to null, the reason I'm not doing node.next is not equal to null is because we end up missing the last element. So if I just write the rest of the code first, what I'll do is change this. So if I did it this way, then we just check for the string and then we return it. What will end up happening is this for loop will exit at the second last node in the linked list. What we want it to do is exit at the last node. So we just remove the child there, because when the child's there, when we try to check if the child node is equal to null, we don't end up visiting that node. It just exits the for loop before it actually reaches that node. If you wanted to do it this way, so we have the child node, we check if the child node is equal to null, then we have to check the strings equal to is this equal here, then we copy and paste the code here again, because the node variable would be equal to that value, and then we also have to take out this node variable and place it up here. So to avoid doing that, what I'll just do is we just make sure that the current node is not equal to null, and if it's not, we can check if this node string is the same as our key which we're looking for, and if it is, we just return this node's value, right? That's pretty simple. If this was node child is equal to null, then we have to take out this variable because so it's in scope, and then right here we have to run this code if we just check if the node's child is equal to null, because we never actually reach the node that we're trying to reach. So yeah, that's the current code. The last function you have to complete is the hash table remove function. Now I'm just going to get rid of all this code right now because we have to be very careful with our logic here. So there's three things that can happen when we're trying to remove a node from a hash table. Either A, we are trying to remove the first node in the hash table, in which case you have to move the pointers around a certain way, or B, we're trying to remove a node in the middle of the hash table, so it has a parent and a child pointer to another nodes, so you have to manipulate the pointers to swap them around. Or C, we are at the last node in the hash table. Sorry, we're in the last node in the linked list, in which case we can just free the memory and set the parent node's pointer to be equal to null. So I'll show you guys what I mean here. The first thing we have to do is iterate over all of the we have to go through all of the nodes in the linked list. So we say hash node is equal to hash table at data at index, while the node's next variable is not equal to null. So we say while node is not equal to null, node is equal to child node. So what we can do here is first check if the key at this node is equal to our key. And I almost forgot something very important. We have to first check if so if the key at this index is equal to 0, so the first node is null, that means no data has been stored at this index yet, so we just return false because we can't remove any data if no data has been stored. Otherwise, we'll run this for loop, and if we find a matching node which has a key, we have to consider all of the cases it has. So let's say the node's parent is equal to null. What does that mean? It's the first node in the linked list. So what we have to do here is make it so that the next node is not the first node. So the way we're going to do that is we're going to first free this node's child, not child, the key. Then we free the value, and then the next thing you have to do is make it so that hash table data index is equal to the next the next node. Actually, my logic here is a bit wrong. So if the node's parent is equal to null and the node's child is equal to null, then what that means is there's only been one node in this linked list. So we can free the memory for key and the value before, and then if the child's equal to null, then we don't have to worry about having to move the pointers around. If it's not equal to null, then what we can do is the node's child will be equal to, we'll say hash table at data at index is equal to node's child, right? And say node's child's parent is equal to null. So that what that will do is, let's say I've got a node here, then I've got a node here, right? And we found our value right here at this node. Well, and the hash table, so hash table at index.date at data of index, this points to this node right here. What I'm doing is I'm making, let's rename the two numbers to make it easier. It points out 1 right now, right? Node 1. What I'm doing is I'm freeing the memory at node 1, and then I'm making hash table at data.index. So this index is going to now point to this node. So that's how we can remove the data if it does have a child node. The other condition we can have is that the node's parent is not equal to null and the node's child is not equal to null. What this means is this node is in the middle of the array or this linked list. So we have to be very careful about how we move around our pointers. So I'll first free the node's key, then I'll free the node's value. And then what I do is I set the node's parent pointer, I'll set the child of the parent pointer to be equal to this node's child, right? So what I've done here is that, let's say I brought back this example, so we say 1, 2, 3, 4, 5. These are all nodes in the linked list. Let's say we're trying to remove element 3. I freed the memory for element 3, and then I've made it so that element 2 now points to element 4. So element 2, so node 2 now points to node 4, and node 4's parent node is node 2. So I've essentially just removed this node from the linked list, and then I also just freed the memory we allocated at this node. Right. The third final condition we can have is that we are at the end of the linked list. So this could mean that we have multiple elements. So what this means is that the parent node is not equal to null, right? However, the child node is equal to null. So what we do here is we just say node's parent is equal to null. Then we just free the node's key and the value, and then we free the node itself. And to be honest, we don't actually need to have this condition here. I'm just trying to illustrate what it means. So in this case, if I bring back the example right here, what this means is that we are at a linked list which has multiple nodes, and we're trying to remove element 5, let's say. So I'm just doing is I'm setting node 4 to point over to null. So this points to null. So this is the new end of the linked list, and then I'm just freeing the memory for this node, so it does no longer exist, right? So that's how we do it. And then once we've done that, we can just return true right here. Or we can also have a case where we don't find the key in this linked list. So this key doesn't actually exist in the hash table at all. So if we don't get any of these values, so I can do is I can just say return true, then return true in each of these conditions. Right, and I think this should work fine. So let's compile it. And we've got some errors. So let's see. Hash node struct. Okay, 54. We have to reference the memory address. 75. What's next? 92. After you reference it. Node's child. Okay, so we have to make it point. We have to make it point to that address. We're not referencing the key, we have to reference the node itself. That was a typo. If I run it, it seems to have been working. Let's see. I just removed this extra code. So I'm expecting surname is to be equal to a 1, but it's not printing that out. So if I open up my debugger here, we can go to this function. I'll set a breakpoint, so let's step into it. F11, let's see. So what index did it generate? Okay, that's strange. I expected it to generate an index of 0 because that's where it's been stored right here. So it seems that we might have made a bit of a mistake. Actually, before I do this, what I want to do is make the hash table a lot smaller, so we have a higher likelihood of collisions. Let's say, so 5 elements. Okay, still doesn't work. Let's see what's going on. I removed this breakpoint, and in hash table add, right here. Does that succeed? Yeah, it looks like we did add the key properly. So let's run. Let's see what's happening here. So the index we get is 3, and the hash table's data at 3 was empty. So let's see. So 3 is empty right now. Yep. So we're storing surname. We're gonna store surname there. Oh, of course it's not working. This should have been hash table.data at index. Still doesn't work? Why not? So if I do continue here, then if I step into it, we have surname index 3. So hash table at data at index. No. So then if I set that, okay. Now this should work. Let's see. So we're gonna get node. Yeah, this should have just been node. Now it prints out correctly. That's good. Prints out correctly. So as you can see, we are printing out the key and the value properly, and then we can also retrieve the key. Then we can also just remove the keys. So it should be working. Now, what I want to show you guys here is that how the data structure is actually made. So if I just make this 3 elements, then I add in a bunch of keys right here. Right, add in a few more. Okay. What I should see is this forming a lot. The hash table should form a lot of linked list data structures. So there's a breakpoint there. Let's delete all of this. So say hash table data. Say 3. There should not be a breakpoint there. Yeah, there we go. Okay, so you can see here we have key AF. So if I open this up, this is empty. So let's see number 2. We have a child node. As you can see, the parent node points back to name, and then if you go to the child node, this one is AFA. You go to the child node, FA. So as you can see, we're creating a linked list to store these extra values, since there isn't space to store each of them separately in a different index. So I hope you guys enjoyed this video. I hope you found it informative and useful. If you did enjoy, if you got any questions, please leave a comment, like, share, subscribe, And I made a video previously about dictionaries in C. So if you're into hash tables, you're probably into dictionaries as well. So you can check that video out as well. And thank you for watching. Bye.